So today we'll just begin with a problem which is basically based on what is known as trans-resistance amplifier or the feedback amplifier. And we know for a trans-resistance amplifier the input is basically a current and the output is, let me just pick this, yeah. Yeah, so for trans-resistance amplifier, we know the input signal is basically a current, okay, and the output signal is basically a voltage. Okay, so with that, we will just quickly move on to the problem, and we'll not discuss about all this connections theoretical part, but rather we'll just get directly into the problem, and we'll try to solve it. Okay. So let us assume a voltage amplifier with a gain value of mu and an input resistance RID and an output resistance R naught. Okay, so all of these resistances are or with respect to the op amp that is being used in the circuit. So let me draw the circuit first, and so let me begin with the current source, which has a non-ideal element Rs, and then we have this inverting amplifier configuration with mu as its gain medium and the feedback resistance value of Rf, and there is a load which is RL. Okay. Yeah. So now for the circuit, we have to identify few things. Let me list out them. So identify the value of RIF, ROF, RN, ROut, and the feedback gain, which is AF. And there is a second quantity we have to find. That is, find the values of all, including those RO and RIs. Okay, so I'm not writing those things, but we will just use them for the case where we have a mu value which is equal to 10 to the power 4 volt per volt, and then later we'll just assume that the value of RID is infinity, input impedance, but the output impedance has a finite value which is 100 ohm, and the feedback resistance value of 10k, and both source as well as the feedback, sorry, as well as the load is assumed to be 1 kilo ohm. Okay, and finally there is a third part which is more crucial in our case. Will be asked to find the voltage gain, even though the configuration that we have here is trans resistance. We'll just try to analyze the voltage gain out of the circuit. So the third part is more important, which we have not seen. So if instead of a current source Is having Rs of 1 kilo ohm, the amplifier is fed from a voltage source Vs with again the same resistance value of source resistance value of 1k. So we need to find the expression for and the value of voltage gain, which is the closed loop gain, which is V naught by Vs. Okay, yeah. So let us try to address each of these things right now. Now, first of all, we have to figure out all this impedances first. Okay, so basically, the feedback network consists of a single resistor whose resistance is marked as RF. Okay, so this is our feedback circuit, and we also will mark the impedances. So it's a feedback amplifier. So whatever the impedance that I'm measuring towards the left of RS would be taken as RIF, but if I skip this RS and if I try to measure, it becomes RN, which excludes the source resistance. And similarly, one could write this impedance as ROF, and if I exclude that resistance, it becomes R out. Okay. So these are the impedances calculated with respect to the feedback amplifier. Okay. But still we have to identify the other impedances like R naught and Ri. These are with respect to the A circuit. Okay. So the A circuit has to be built by moving all these non-ideal components onto it. So we'll just do that one by one. And so first let us begin with the discussion of this beta network. So we know that this beta network, yeah. So first of all, we have to see like what type of sensing and what type of mixing has been done. Okay. So probably by the end of this today's session, let me try to give some sort of simple cases in order to identify the type of mixing and the type of sampling that is done by the feedback network. So in this case, obviously, you could see that this V naught is being directly sampled by this source resistance. Okay, so which means that the type of sampling that we are doing is a voltage sampling, and in order to do a voltage sampling, we could think about a voltmeter which measures the voltage through two probes, which means there is supposed to be a shunt. Okay, so the type of connection that I have at the output is basically a shunt. Okay, and what has been mixed at the input is basically a current. Okay, so here what we are trying to mix is a feedback current, and yeah, the feedback current has to move up. Yeah, and the value of Is would then come over here, and there is a reduction in the value of this current II. Okay, so now clearly you could see that this particular point where our feeding the signal as well as we are trying to feed the beta network's terminal will actually gives us a notion that it is going to have a current mixing. Okay, so that is how one could quickly end up having a result for it. Okay, and do not get an assumption that just by looking at the type of source that we have, we can conclude the type of mixing that we are doing at the input. Okay, so that is not always the case. Okay, so let me try to work out this particular problem, and at the end of the class let me try to explain what how one could quickly identify the type of mixing and the type of uh, sampling that we are doing at the input and output respectively. Okay, so as we have figured out that the resistance RF is the one that creates a kind of beta network or the feedback component. So and we know that we are trying to sample a voltage. So let me try to fix that voltage source of V naught, and we are trying to get a current through it, right? And the current is basically in the opposite direction as it is denoted in this particular diagram. Okay, and yeah, so basically they create a loop in order to have this. Yeah, so now that we have this, and now let us try to find the relation of beta, where beta is something that has to have a relation of an input being V naught and the output being IF. Okay, so we need to find out those results. So it is pretty clear that a V naught could be written as something like RF times the current flow, but since the current is flowing in the opposite direction or towards this positive potential of V naught, it is written as minus IF, okay, with a negative sign. and now when we try to check the value of beta, it becomes minus 1 by Rf. Okay. So, that is the value of beta that we have got, and now we have to figure out what is the R11 and R22 impedances out of this beta network, right. So, for which we have to know the knowledge of the type of connections that they make at the input and or across the port 1 and port 2 of the feedback structure. So, let me again just draw this feedback network and have this resistance Rf, and let us begin with the computation of R11, which we really want to compute from the port 1. Okay, so this is my port 1 and port 2. Now, since because we know that this port 2 is making a kind of shunt connection, the way that one has to find the impedance across the other end of the port, which is the port 1, is by making this shunt to act to go as a kind of short circuit, right. So, let me just try to do that. Uh, yeah. So, I short circuit this shunt connection, and then I am trying to measure the value of this R11. So, clearly from here it is, one could state that the value of this R11 is equal to Rf. Okay. So, now let us try to figure out the impedance value of R22. Now, uh, yeah. So, clearly one could see that there is a connection that we make with this feedback network here. Okay. Yeah. The this is the type of connection that we use for current mixing. So, the type of connection that is used for current mixing is again it's a shunt type. Okay. Now, even this connection is also a shunt type connection. So, again one could use the same analogy of finding out this R22 impedance. So, we have this Rf and we have port 1 and port 2, and while trying to compute the value of R22, the port 1 has to be since because it is a shunt, okay, since because it is a shunt, we have to short circuit that particular terminal, and due to which we will end up having the value of R22 to be equal to Rf. Okay. So, having got these impedances, let us try to draw the structure of a circuit. Okay. So, which has to be derived from here now, and includes all this impedances of Rs and R11 towards the input, and Rf and the so it is basically the RL and as well as the R22. Okay. Yeah. So, let us begin with the structure of this A circuit, and we know that the input to this is basically a current, because it is a trans resistance amplifier, and we know that the input is basically a current I and the output is basically voltage. Okay. So, we need to remember those things now, and the gain of this trans resistance amplifier is defined as the input, which is II, to the output voltage V naught. Okay. So, with these things in our head, let us try to move all these impedances, and we know that the source resistance Rs can be brought directly, and the value of R11, which is basically equal to Rf, that also goes in parallel, and we also have an impedance which is equal to RID. Okay. So, that is the input impedance of the op amp. So, if you want, I can just draw this. Okay. And we know that this negative terminal, sorry, the positive terminal of this op amp is directly connected to the ground. Okay. So, let me just bring out this connected to the ground, and we have the positive here and a negative here. Okay. So, we will just remember this such that while trying to compute the gain, the type of op amp configuration that we have used is an inverting amplifier configuration. Okay. So, now what we have is a kind of voltage amplifier. The op amp, as I said in the last class, it is always taken as a voltage amplifier, and which means that we have to have a voltage dependent voltage source. So, in order to have this voltage dependent voltage source, let me just mark the diamond shape. Okay. And the value of this is given as mu times that of the voltage drop across this resistance RID. Okay. Now, since because it's an inverting amplifier, I use a negative sign of mu, and the voltage drop across this RID is measured as something like VID. Okay. So, it is the same voltage drop either across RID or RF or RS. Okay. So, it does not matter, just because the input is a current, and due to which the voltage drop of any of these resistances would be same. Okay. So, let me mark it here, and that is the one that is being sensed by this particular circuit, and it's an inverting amplifier, and due to which we have added a negative sign here, and this has a specific value of output resistance, and let me mark that output resistance as R naught, and at the output we have connected a load. So, let me just have a load, and we also have to add the resistance of our uh, feedback R22, and we know that the value of R22 is basically just RF, and we have this output voltage V naught. So, now using this A circuit, let us try to evaluate the value of this RO and RI. So, as I said, the value of RI is nothing but the input impedance of an open loop circuit, and the expression for RO is supposed to be the output impedance of a open loop circuit. Okay. So, now in this case it is a pretty straightforward way of computing this value of RI, which is nothing but the parallel combination of RS, RF and RID. Whereas when it comes to this R naught, first of all we need to kill the input source, right. So, in this case the input source is a voltage, sorry, it's a current II, and a killing is nothing but it's open circuiting it. Okay. So, when there is an open circuit, no current flows through the circuit, so due to which I becomes 0, and one would not measure any type of drop across this resistance, and since no current flows, the voltage across this VID will be equal to 0, and due to which this current controlled, sorry, a voltage controlled current source is taken as a 0. So, which means that I can kill this voltage source with a short circuit. Okay. So, due to which what happens is that we end up having a resistance value of R naught, which is the parallel combination of R naught, RF and RL. Okay. So, these are the input and output impedance of the A circuit. The next thing is that we need to calculate the gain of this particular circuit. Okay. So, we need to evaluate the value of A, and it is defined as V naught divided by II. Now, one could evaluate this expression just by knowing the relation that we have between this II to VID, and then onto this V naught. Okay. So, first let me just try to evaluate the value of VID. Now, this VID is nothing but the current II that flows through this total input impedance of Ri, right. So, I could write it as II times that of Ri is my VID, or the voltage drop across this resistance RID. Now, in order to calculate this V naught, we already have a voltage source. So, one could use a simple voltage division rule that would give us the expression for V naught. Okay. So, V naught is defined as RF in parallel with RL, and that is the drop across which the voltage V naught is measured, divided by the summation of R naught plus this parallel combination of RF and RL multiplied by the source potential, which is given as mu times that of VID. Now, in the place of this VID, one could drop out the expression that we have evaluated here in terms of II times Ri. Okay. So, let me just quickly just grab this expression, copy and then put it here. So, now that I can replace this VID in terms of II times that of Ri, and now that I can just use this Ri or drop this term Ri to the denominator, so that this gives me an expression for the value of A. So, it is this quantity that gives me the capital A letter or the gain expression. So, now we will also try to evaluate the expression for A beta, so that it becomes pretty clear as we move on. So, the factor of A beta, which is nothing but the loop gain, can be written as A, which is nothing but minus mu Ri into Rf in parallel with RL divided by R naught is Rf in parallel with RL. Okay. So, this is my quantity A, and we know that the factor of beta is nothing but minus of 1 upon Rf. Okay. So, these two negative signs can then be cancelled out, okay, and one would end up having a mu times that of Ri divided by Rf into this entire huge expression. Yeah. So, now that we got the value of A beta as well, now let us try to evaluate the feedback amplifier gain, which is defined as AF and V naught by IS. Okay. Yeah. So, that is always defined as capital A divided by 1 plus A beta, and now that we have already computed all of these expressions, so it is just a simple substitution of A at the top and yeah, Ri, and then Rf parallel with RL. Yeah, so it's a pretty lengthy expression. Yeah, so I'm just going to multiply this entire quantity by a factor of, I guess, yeah. So this gives me the A beta term. Okay, yeah. So now, in case if at all, if there is an assumption that the factor of A beta or the loop gain is much larger than the value of 1, then one could do some sort of approximation out of this expression. So, clearly, if I drop out this particular one, then there are most of the terms that are common, and when we try to short out all of those terms, we end up having this closed loop gain being written as minus Rf. Okay, so clearly the unit of this A or AF will be in terms of V by I, whereas the beta will have an inverse relation which would be like I by V. So, that is the unit of beta. So, that when one tries to multiply this A times that of beta, it becomes a unitless. So, there is something that I forgot to mention even in the previous class. The loop gain always supposed to be a unitless quantity. So, in this case, when I try to multiply A, which is having a unit of V by I, and beta, which is having a unit of I by V, these units in general they tend to cancel each other, and due to which we will get a kind of number out of this uh, A beta. So, in general it is a dimensionless quantity, the loop gain. Okay. So, this is applicable for any type of amplifier. It can be a voltage amplifier, it can be a current or transconductance or transresistance, whatever it is. The A beta term is always a unitless. Okay. Yeah. So, now that let us try to compute the value of RIF and ROF, which are the feedback amplifiers input and output impedances or the resistances. So, we know that there is a shunt connection that appears across the input side. So, due to which whenever we have a shunt, uh, the open loop input impedance will be reduced by a factor of 1 plus A beta, or the amount of feedback. Sorry. Yeah. So, now that I am just going to rewrite this expression in a quite uh, different way in order to ease the calculation of this RIF. So, let me just write it as, rather than writing it as RIF, I will write it as 1 by RIF, so that one could write this expression as 1 upon Ri divided by A beta times that of Ri. So now that I'm just going to substitute all of these expressions that we have computed, A beta is nothing but mu into Ri divided by Rif. So that would get cancelled with this one of the Ri. So we would end up having Rf at the bottom across the numerator, and we have this huge expression of RL Rf parallel combination, and this RL. Okay. So now clearly you could see that there is a resistance divided by a resistance. So this becomes a unitless. Okay. Now this ratio, since because it's a unitless quantity, what I can do is that mu is again a unit dimensionless quantity. I can just combine with them such that this entire one that I have circled will become some sort of dimensionless quantity here. Okay. So it is something like I could relabel this entire expression as mu prime, and due to which I can rewrite this quantity of 1 by Rif as 1 by Ri plus this mu prime, which is a unitless dimension, divided by Rf. Okay. So this means that the input resistance Rif could be written as Ri in parallel with Rf divided by this mu prime. Okay. So this is something that one could quickly end up having this result. Okay. Now again there are a few more simplifications that can be done just to eliminate the source impedance here. Okay. So due to which I will try to expand this Ri. We know that the value of Ri is a parallel combination of RID, Rf, Rs, and along with it we have this particular term that comes, which is Rf divided by mu prime. Okay. Yeah. So this is our total Rif, and since because we want to compute the value of Rn, where Rn is supposed to exclude the source resistance, we have rewritten this expression for Rif as something like parallel combinations. Okay. So now here again what one can do is that one could actually combine this and these two factors into a single component, and so due to which I just rewrite as something like Rs, and then that goes in parallel with Rf with mu prime, and since because it has a value of 1 at the denominator, one could rewrite this as to be something like Rf divided by mu prime plus 1. Okay. Now the value of Rn is something that we need to exclude the Rs from Rif, right. So it is something like I have Rif and we need to eliminate this quantity of Rs out of it. Okay. So in short, I can evaluate the value of Rn, where it can be written as Rif minus this Rs. Okay. So it's a direct exclusion, and due to which one would end up having these impedances to be written as 1 by RID plus mu prime plus 1 divided by Rf. Okay. And that is nothing but our Rn, and an inverse transformation of this 1 by Rn will give us the value of Rn itself, which is the parallel combination of RID in parallel with Rf mu prime plus 1. Okay. Yeah. So now that we got this expression of Rn, and again there are a lot many things that one could do. If at all, if this value of RID is assumed to be large, then this factor becomes small, just because Rf is basically diminished by a gain expression here. Okay. And due to which, if this RID is comparatively larger than this entire factor of Rf by mu prime, then one could approximate this Rn provided RID is okay. So in that case one could write Rf divided by mu prime plus 1, and again if mu prime is much larger than the value of 1, then it could be rewritten as something like this. Okay. Yeah. So now let us come back to the calculation of this ROF, which is the feedback amplifier's gain, the output impedance, and that is written in terms of output impedance of a basic amplifier divided by the A beta, just because we have a shunt connection at the output, and whenever we have this shunt connection, it is always better to write their impedances as one upon this ROF, and this could be written as something like this. Okay, so now again we know that the value of this A beta is written as something like Ri by Rf, and we still have this R naught sitting here. So, and we have something like Rf in parallel with RL. Yeah. So this is what we have, and we also have to remember that this factor R naught is nothing but it's a parallel combination of RL, RF, and R naught, and if at all if I am combining this expression as a single quantity, then the parallel combination of this one and the second term can be written as something like I think it becomes too much of messy. I'll just write it in terms of 1 upon form, so that this 1 upon R naught form can be rewritten, so that I can directly use this result over here. Okay, so due to which I'm just writing it as in terms of 1 upon R naught form. Okay, yeah. So what I have here is that okay. So this is what I have uh, for the place of this R naught. Okay. So now that there are a few common terms that one could use over here in order to cancel them. Okay, and one of the thing that we can do is that we can cancel out this term with the numerator term, and there is also one more common term that we have, which is RF in parallel with RL, that can also be removed. Okay, so at the end what we have out of this expression is just this R naught plus this mu times Ri divided by Rf. I think there is a factor R naught that is coming out from here. Okay, and so again this could be rewritten in terms of this, so it can be written as 1 by RL plus 1 by Rf plus 1 by R naught. Okay, and this new quantity, which is mu divided by mu into Ri divided by Rf into 1 by R naught. Okay, so again this is a kind of ratio that I have, so one could use this ratio factor things, and so I have this weird combination, not across this one, let me use this one and this quantity. Okay, yeah. So let us use this quantities in order to combine, and doing so the value of ROF can be written as something like RL in parallel with RF in parallel with R naught divided by 1 plus mu times that of Ri divided by Rf. Okay. So this is what I have, and yeah. So from here one could evaluate the value of R out again by using the same math. I need to exclude this, so excluding that would result in Rf in parallel with R naught divided by 1 plus mu times that of Ri divided by Rf. Okay. So all of these things that I have shown here is a very straightforward method. One thing is that you need to work out to really check whether whatever we have done is right or wrong. Okay, yeah. So now let us try to compute the numerical values based on what was given. Okay. Now for the case for numerical values that are given, the value of input impedance of the basic amplifier Ri can be written as uh, again I'm rewriting this RF and RS, and we know that this RID is taken as infinity, and that goes in parallel with 10k, and RS is having an impedance value of 1k, and all of these combinations will end up having a value of 0.91 kilo ohms. Okay, and similarly the output impedance of the basic amplifier can be written as R naught in parallel with RF in parallel with the load impedance, which is RL, and again we have the load impedance to be equal to 1k and RF being 10k and the R naught being 100 ohm. So I will write it in terms of 0.1. So everything would be having a basic unit of k kilo, and that would end up having a result of 90 ohms. Okay, so that is the output impedance of the basic amplifier. And now uh, we still need to compute the basic amplifier's gain, which we okay. So this is the expression that we have got earlier, and just using them directly here. Okay. And the value of mu that is given is 10 to the power 4. So I'm using that, and the value of Ri that we computed, which is 0.91 kilo. So I'm just not using the kilos here. So at the end I will just add them, and this 0.1 and parallel combination of this quantity. So finally one would end up having somewhere around 8198 k ohm. Okay, and right now the factor of beta is nothing but 1 upon minus 1 upon RF, which is basically divided by 1k, and that results in 0.1 millisiemens. Okay, and now the factor of A beta can be written as this quantity, and 1 plus A beta is just the addition of 1, which is 820.8, and the feedback gain, which is, sorry, there is no point here, divided by 820.8. So again we should not forget the factor k with respect to the gain A, and that results in 9.9 kilo ohm. So this is something, a value that is closer to the feedback impedance. Okay, so normally this is a basic, like one could write this amplifier gain to be approximately equal to 1 by beta, and we know that the factor of beta is written as minus 1 by RF. So due to which when we plug in here we would end up having the value of RF, and we know that this value of RF is equal to 10k. So this value of 10 kilo ohm is approximately equal even when we try to substitute the values of A and stuffs. Okay, so these two values are almost same. So one could have used this formula to directly get it, but still we went a long way to show that the value is a bit closer, and the reason for this close value of this expression with this normal expression is because the factor of A is quite larger, which is almost 8188 kilo ohms. Okay, so that is a very large quantity, and due to which we are getting an expression or the gain of the feedback amplifier which is closer to 1 upon beta expression. Okay, yeah. So still we have to find out the value of RIF, which is written as Ri divided by, and it is 110 ohm divided by 820.8, and that results in 1.1 ohm. Okay, which is a pretty small resistance that we end up, and now that it has to be excluded from this RIF, excluding the source resistance, and we know that the source resistance had a value of 1k, and due to which let us try to plug in all of these values, and as you could see that this quantity almost closer goes to a value of 0.001, right, and due to which there is no much difference between this RIF and RN, so we would end up having approximately the same result as that of RIF. Okay, so now the final expression for ROF can be written as RO divided by 1 plus A beta, and which is 90 divided by 820.8. So that should give us this quantity, and the value of R out, uh, typically the same sort of expression, and we finally get a value which is almost closer to the value of ROF. Okay, so now that we are moving on to the third part of our question, which is basically the computation of the voltage gain. Okay, now what was said is that in this particular problem, if this combination of current source with the resistance is being replaced. Okay, let me, if possible, let me just copy the circuit. Yeah. So now we are addressing the third part of our question, and in the third part, what has been said is that if we could replace this IS with a voltage source, and not as a shunt resistance, but rather as a series resistance RS, what would be the voltage gain out of the circuit? So we want to compute the factor of AF, which is defined right now as V naught by Vs. Okay, so previously we computed the feedback gain as V naught by Is, but right now what is being asked is the computation of this. Okay, so now one no need to recompute all of these things with uh, uh, like computing the factor of A and stuffs. Okay, so all of these things need not to be done, just because uh, you see the type of feedback network that we have still has the same sort of connection, like shunt at the input and for mixing the current, and shunt connection at the output for sampling the voltage. So those are the information that stays the same, but how would one can compute the value of Is in terms of Vs? Okay, so that if could able to identify, then the entire process of computing the gain becomes much simpler. Okay, so now what I am trying to say is that the relation between this Vs and Is is what we need to compute, and one knows that one could find out this, if at all, if the current that flows through this Rs. Yeah, so I think it's a kind of Thevenin's equivalent voltage component that we need to find. Okay, so just the product of the Is into Rs will give us the value of Vs. Okay, so now in a way one could rewrite this gain, which is a new gain. So I just don't want to write it as AF, but rather I just use it as VF. Okay, so now that in order to get this out of this expression, let us use this simple rule of converting Vs, which can be written as Rs into Is into V naught, V naught being at the top. Okay, so we know that this expression is nothing but our AF. So just dividing this value, and the value of AF that we computed was equal to minus 9.99 kilo ohm, and that if it is being reduced like divided by a 1 kilo ohm resistance, the resistance value would then cancel, or basically the units of ohms will not be there, just because it's a voltage by voltage term, and finally we end up having a voltage gain of minus 9.99 volt per volt. Okay, so yeah, so now as I said here, in this case one cannot judge the type of feedback based on the type of source that we have. So here in this case there is a voltage source and there is a series resistance, but that will not assist us in making the gain expression of A. Okay, so one has to see like what type of mixing that has been done and what type of sampling that has been done, and based on that one has to arrive at the type of A circuit, whether it is a voltage amplifier or it's a trans conductance or trans resistance or current amplifier. Okay, so all of these information has to be derived from by basically looking at the type of feedback network that we have. Okay, so hopefully this is you would have understood a lot. Now let me stop here, and I'll just get back into the WebEx, and we'll just meet there. Thank you.